Thank you everyone for joining us today. In this session, we're going to be discussing the basics of dust collection system design for agriculture. My name is John Daniel. I lead up our corporate efforts to support engineering firms here at Donaldson. We also have Amy Miller on with us today. She's our training manager, and she'll be working behind the scenes and will be moderating our Q&A at the end of the session.
Thanks to everyone for joining us today. So please submit your questions into the chat box as you think of them throughout the webinar, and we'll address them towards the end of the session.
Yeah, thanks, Amy. We're going to start off the session today reviewing some of the common agricultural processes where dust collection is usually needed. Then we'll get into the four primary components of dust collection system design: hoods, ducts, collectors, and fans. And at the end, we'll have a Q&A session to answer some of your questions that you might have and put them in the chat box. Please note it can take years of education experience to become an expert in dust collection system design. The goal of this session is just to give you an overview of the basics. In case anyone here isn't familiar with Donaldson, we've been solving customers' complex filter challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of advanced filtration technologies, and we excel at producing high-quality filters and collection equipment. We pride ourselves on having a global reach and a local touch. Our world headquarters is in Bloomington, Minnesota. We have about 55 manufacturing plants and 21 distribution centers around the world. Before I introduce our featured speakers, I want to quickly explain how to engage with us. As Amy mentioned, please enter your questions into the chat as you think of them, and we'll be able to answer them at the Q&A session at the end. And during the webinar, we may ask a question or two, and you can respond by putting a thumbs up or thumbs down by clicking the icon at the bottom of the screen. And with that, I'm pleased to introduce our featured speakers today: Charlie Cooper, who's a territory manager with Donaldson. Two individuals he works frequently with from Fluid Engineering, an authorized dealer partner of ours in Birmingham, Alabama, Anthony Martin and Andy Hammer. Anthony is a licensed mechanical engineer and graduate of Clemson University. In addition to 8 years at Fluid Engineering, he also worked as a maintenance supervisor and director of operations at the peanut shelling industry.
Thank you, John. Happy to be here, talk with all of y'all about dust collection design in agriculture.
Yeah, thanks, Anthony. And Andy is a graduate of Purdue University. He spent 14 years after graduation in various industrial manufacturing settings and spent the last 10 years working with Fluid Engineering, focusing primarily with air pollution projects in the agricultural segment.
Hey, John. Yeah, thanks for having us today.
All right. And last but not least, we have Charlie Cooper, who spent over 25 years in industrial sales, most recently the last 10 years with Donaldson. He earned his bachelor's degree and master's degree from Louisiana State University. Charlie lives in Baton Rouge, and his territory includes Louisiana, Mississippi, Alabama, and Tennessee. Take it away, Charlie.
Thanks so much. I appreciate it, guys. Hey, first of all, let's get started by just finding out the experience level that people have with dust collection design. Feel free to choose one of the reaction emojis below. You're confused about which one to choose. I prefer the rabbit. I'm always looking for up-and-coming projects.
All right. Looks like we're getting a few with a little bit of experience, some with none. So it looks like you got a little bit of a range, but looks like you have a broad range of experience here.
All right, great. Sounds good. All right, let's take a minute just to talk about the dust generated during agricultural processes. Why is dust collection important? First of all, we want to improve air quality. It's super important to have good air quality, and we want to control exposure control for the operator. We want to make sure that breathing zone is clear from dust and everybody stays safe. Next one would be environmental concerns. Anytime a dust is generated and goes to a dust collector, we want to make sure that the air coming out of that dust collector is clean. Many times that's regulated by EPA or someone along those lines. We have safety and hazard concerns. One of the big ones here is combustible dust. So we always turn to NFPA rules and regulations for that. We want to make sure we can mitigate for fire and explosion protection, again, to keep people safe. Cleanliness is really important. Some of these processes can actually generate a tractor truckload of dust a day. So that dust, you can imagine if it just piled up into the facility, how that would be a complete nuisance. It's also important to keep dust down just so we can help all the other machinery in the building, like fans and motors. Dust can get into those systems and really wreak havoc. Another one is reintroducing the dust that's there to be collected. It's important to be able to capture this dust. Sometimes this dust has value. Here's some examples of agricultural facilities. So we have grain elevators, inland terminals, export terminals, ethanol plants, flour mills, seed mills, and in seed mills you could think of almonds and peanuts, and even we have facilities like sugar mills. Most of these facilities have different processes, and each one is kind of unique. For those of you that are kind of newer to this process, here's a good grain process map to show you how grain is brought into a facility and how it goes through a facility. The blue dots represent where dust collection would need to occur to make sure that we keep everything clean and everyone's safe. You can see we have dust coming in or grain coming in from trucks, rail, and barges. Then it's sent to a conveyor. Occasionally it goes to a dryer if necessary. From the dryer, it goes to the bucket elevator or an incline conveyor. Then it can go to a cleaning system. You'd really be surprised all the different stuff that gets into grain, dirt, trash, all kinds of stuff. We want to make sure we clean that. Then it would go to a turn head or a tripper. Here, the grain would be sent to different locations or different bins throughout the plant or facility. So we go to storage bins. From the storage bins, it would go to the scales, and from the scales, it would leave either on truck or rail, or maybe go to a different process within the plant. Here's an example of a rail dump. You can see the rail car comes into the facility. It has a pit below where the rail car can actually dump into the pit below. The pit below will have dust collection on it to be able to keep that area under a negative. This will prevent the dust from escaping. Here's an example of a truck dump, very similar to a rail car dump. In this video, you can actually see the dust coming off of it. And this dust would be much worse if it wasn't for the fact that we had dust collection underneath this. You can see this one on the picture on the left, that we actually have that ducted to a collector outside. So it really depends on the application and if they can have a pit dump where they can have dust collection from the bottom, or we can do it from the sides. Here's an example of convey belts. Anytime there's a transfer point or conveys, we want to make sure we have that conveyor under a negative to prevent dust from escaping. These are two examples of point source captured dust collectors. The good thing about these collectors is that they capture the dust and they put it right back into the process, so we don't have to worry about having to deal with that after the fact. It's important to make sure that these dust collectors are a little ways away from the transfer point so we don't re-entrain dust. Here's a stripper or turn head. Again, this is where you could send dust to multiple bins. You can see the bins down below, and this just lets you transfer it to different areas throughout the plant. Here's a couple of bin vent applications. Here, anytime you load grain into a silo, we have to deal with the displaced air that creates. So this lets the air escape and contains the dust while that happens. Again, the good thing about these type of collectors is the dust is put right back into the process. Here's a picture of a ship loader. If you look closely, you'll see maybe 7 or 8 small collectors there, maybe a couple of cyclones and a couple of CPVs. These again are used on the conveyor belt to be able to keep that conveyor under a negative so dust doesn't leak when we hit transfer points. And also we have some at the end of the ship loader. When the dust hits the bottom of the ship where it's loading, it creates a plume, and these collectors will help. Again, these collectors put the dust right back onto the conveyor or back into the ship. Truck loading is very similar than truck unloading. Here, we're just doing it from the top. If you look at the picture in the top right-hand corner, that's a couple of point source dust collectors. When this process is being done and the truck is being loaded, actually we can have the truck finish loading, then we can just wait a few minutes and this will pulse the dust right back into the truck, and it's a way of capturing that value of the dust. Now I'm going to turn things over to Andy and Anthony, and they're going to talk about the basics of dust collection systems design.
Yeah, thank you, Charlie. So here's a very simple diagram of a typical dust collection system. You can see on the right, there's a fan that creates airflow, which is used to capture dirty air through a hood. That dirty air is then conveyed through a series of ducts to a dust collector. Here the contaminated is separated out and the clean air passes through a filter media to the fan where it's eventually discharged into atmosphere. These systems are some of the individual parts. We design these systems based on the characteristics of the dust for the various applications and the various processes. It's important to note that if one component is poorly designed, the entire system can be negatively affected. So when we design systems, we have two main objections. One is we want to capture the correct amount of CFM that's required to control contaminants or fugitive dust from the point of generation. And the second thing is while we're calculating that CFM is to keep in mind the total energy or horsepower that's required for those airflows. The publication shown here is the Industrial Vent Manual, the Industrial Ventilation Guide, which is an indispensable resource for proper system design. The Vent Manual was written by the American Conference of Governmental Industrial Hygienists, which is a nonprofit scientific group organization that advances occupational and environmental health. If you're interested, this group puts on several courses throughout the year that use this textbook as a guide. And these guidelines are consideration by most in the industry, including OSHA, to be a proper standard for ventilation design. So there are many different factors that we take into consideration to help select and size dust collection equipment. The first is the size and characteristic of the dust, whether it's small, large, heavy, light, fluffy. Is it agglomerative? Is there things that does it become sticky? The second is what type of equipment or process that's producing the dust. It's extremely important to understand how adding a dust collection system may or may not affect the customer's or end user's process. The third thing is if the process is continuous or if it's intermittent. We need to know if we're capturing a 5-gallon pail of dust per day or a full tractor trailer load. And then what we're going to do with the dust once we collect it. We're going to drop it into a drum or bucket. Are we going to convey it pneumatically or mechanically to a storage hopper? Or, as oftentimes we do in the agricultural world, are we going to reintroduce that dust right back into the system so it continues on? There's two things, or the last two things we look at is the total cost of ownership. So upfront costs versus long-term maintenance and reliability costs. And then last but not least, we always need to consider the if the dust is combustible or not. So generally speaking, dust generated in the agricultural process is most likely combustible. As such, it may pose a risk of fire, flash fire, and explosion. I'm sure you're all familiar with the fire triangle shown here, but if you look at the bottom left-hand corner of the slide, fuel and oxygen, or if you have fuel, you have oxygen in this ignition source, that's what can produce a fire. When that source of fuel is a dust or finely dispersed dust, it can lead to a flash fire. And then when that dust is then contained within, say, a dust collector or a bucket elevator or a totally enclosed belt conveyor, the conditions are right for an explosion. We'll circle back around to combustible dust and NFPA towards the end of the presentation here, but wanted to get that into our section here. So a lot of different formulas that we use when we design a system, the most basic of which is Q equals V times A. That's where Q is the volume of air flowing through a system. In the United States, we use cubic feet per minute. The V is the velocity or linear speed of the object, which is in our case, it's the area of the ductwork that's conveying that dust. This formula is one of the basic building blocks of a dust collection system. So we start at the pickup point. We capture the correct amount of air that's required to contain the fugitive dust, and we design a hood to accomplish that. It's probably one of the most important parts of the dust collection system is the hood. And properly, great design dust collection system, and if you mess up on the hood, you're not going to capture any of the fugitive dust. So here we'll have Anthony, and he's going to talk about the first component of the dust collection system, or dust collection systems, which is the hoods.
Thank you, Andy. Yes, the hood is very, very critical to the success of the dust collection system. We're going to talk a little bit about the hood design. So a lot of times in the grain industry, we're trying to keep the equipment under a negative, or we're trying to capture that fugitive dust that's coming off from a transfer point. We size for the in-draft velocity if it's an open belt conveyor or if it's a dump pit. We look at the grain volume. 1 bushel displays 1.25 cubic feet of air. Poorly designed transitions are going to entrain a lot more air. So we're looking at, how steep is the fall? What does the transition look like? The objective is to only collect dust. We don't want to capture any grain. We want to keep that in the process. Some common mistakes we see, the wrong style of hood, hoods in the wrong place, and then improper airflow, whether too much or too little. A general rule of thumb for capture velocity is about 500 to 800 feet per minute at the hood face, assuming it's designed correctly. If the hood is closer to the grain stream or the hood is closer to the dust generation point, we're going to lower that face velocity so we don't pick up product. Good example of that, when you're on a belt conveyor and you've got the transfer coming on the belt conveyor, if that hood's too close, that grain's still kind of bouncing down as it settles, and we want to make sure that our face velocity is low enough not to pick up the grain itself. Grain dust needs about 200 feet per minute to get pulled into the hood. Anything less than that is going to kind of settle out and won't get pulled up into the hood. When you're designing hoods, you want to avoid airflow extremes. Too much airflow at the hood, you've got the potential to capture good product. It also increase your cost because it's going to have require more static pressure to move that air. And then too little airflow at the hood, we're not going to be able to collect the dust itself. We're going to have additional housekeeping requirements, and then of course increased dust in the facility. Charlie kind of talked about some of the applications. We want to talk about some of the hoods that we use here. When grain comes into the facility, it's typically coming via hopper bottom rail car or hopper bottom trailers. The dust generation is the highest when they first open the gate, and we want to make sure that our operators understand that they've got to fully open the gate. We want to choke feed the dump pit. If the dump pit is deep enough, you can utilize above the grate ventilation, which is shown in the left-hand picture. We typically size these for 200, 225 CFM per square feet of open area. A lot of times these will have baffles in there. The underhoods have to be located far enough away from the grain pile so that product isn't picked up. If the dump pit is shallow, or there's some other issues underground that we can't utilize that under the grate ventilation, we do use side draft hoods. Now these would be on both sides of the truck. We typically see this more in truck applications. You want these to be as close as possible to the hopper bottoms. Most of the hopper bottoms have two hoppers on it. So this picture on the right is set up for that truck to come in and the operator to be able to empty both hoppers without having to move the truck. We typically see 10,000 to 15,000 CFM on these systems, but it's really application dependent and how close we can get those hoods to the hopper bottom itself. Belt conveyors, grain industry has a lot of belt conveyors. Andy talked about the industrial ventilation manual. They have a lot of VS plates with designs for providing dust collection on different types of equipment. This is one VS plate for belt conveyors in particular. You can see here in number 3 where you've got a chute to belt transfer. The collection point is going to be 24 inches above the belt. It's going to be spaced far enough away from the chute to allow that material to settle out. And then it's sizing it for 500 CFM per foot of belt width for belt speeds over 200 feet per minute. The difficult part with grain facilities is there's a lot of times restrictions in the way. We're retrofitting dust collection into grain elevators. And this is where it's really important to understand, what velocity the grain gets picked up at, what the vent manual is trying to really get across. This is just a few examples of some belt conveyors underneath in the basement of some grain elevators. Picture on the right, the hood's off to the side because there's obstruction overhead. So we've got to get creative with how we design these hoods with existing systems. I do want to highlight, though, the picture on the left. With most of the dust collection systems we do in grain, we utilize blast gates to balance the system. You never want to put a blast gate right at a hood. If you do that, you're going to have excessive velocities, more so than we designed for the face velocity. It's going to create turbulence in there, and we're going to pick up product that we don't want to pick up. Bucket elevators. The most dust generation that happens at a bucket elevator is at the tail pulley. The picture on the left has 2 hoods right above the tail pulley. We've kind of gotten away from that design, and we're moving the hoods up the up leg about a third of the way up. And the reason we're doing that is as grain's going into the buckets, it's still agitated. We have a chance to collect the material and not just the dust. So by moving the hoods up the elevator leg, we're able to capture the dust and not the product. We're also able to exhaust more dust than we would have at the boot itself. The picture on the right was one we'd retrofitted, and that's the reason why you've got 2 sets of hoods. We had some face velocity issues that necessitated us doing that. But with that, when you're pulling off the up leg, you want to balance the airflow on both sides, so that way the belt's not being pulled to one side or the other. Get the belt rubbing against the casing, buckets hitting stuff, potential to create sparks. So you always want to make sure that airflow is balanced there. Andy kind of mentioned, I think Charlie did too, that a lot of times the dust has value, that the customer wants to recapture that dust and put it back in the process. We never want to return dust at or before a bucket elevator. This is this is where we have the greatest risk of an explosion in the facility, and we don't want to add more dust to that process. We also don't want to return it around any machinery where it can be drawn back into the system. We always want to return it downstream of where it was first collected, or send it over to a dust bin for pelletizing or whatever else the customer may want to do with it. One of the things we don't want to do is stub the ductwork directly into the equipment. These systems operate at 4,000 feet a minute. Some of the older systems before NFPA became really big in the grain industry, they were sized for 3,500 feet a minute. At those velocities, we're going to pick up material. And so for these hoods to actually work, you've got to reduce the airflow. You're going to have settling in the ductwork, and you're not going to get the performance out of your system that you were looking for. So after we've sized our hoods, we've come up with the airflow that we want to do. We've routed the ductwork back to the collector. We've got to do some design to get the dust from the hoods to the dust collector. I do want to highlight something. We're not really going to go into detail on it today. The static pressure is always balanced at the branches, excuse me. So the static pressure coming from the hood on the left and the static pressure coming from the hood in the center has to equal out. So the static pressure associated with the pressure drop of the airflow through the hood, static pressure associated with the pressure drop through the ductwork, the elbows, all that has to balance out. So in this system, the hood in the center is going to pull a lot more air than the hood on the far left, just because it's got a shorter path to get the dust collector. It's a canopy hood versus a slotted backdraft hood. This is where, when we talk about balancing the system, we're going to put blast gates in to help us get air to the right place and to balance those systems. A properly designed ductwork system should pull the minimum airflow we've designed from each hood. The velocity should all be sufficient, that 4,000 feet a minute, and we're trying to use the least amount of energy to get it from point A to point B. Some common mistakes we see are the incorrect duct type, incorrect duct size, and then the system being unbalanced. We really try to shoot for that 4,000 feet a minute in all of our duct branches. Typically, we're going to see duct velocities between 4,000 and 4,500 feet a minute, depending on, especially as we go up in sizes where we've got multiple branches coming together, it may be a little bit over 4,000 feet a minute. If the duct velocity is too high, it will require more energy to move the air through the duct. It's also going to create other issues like noise, abrasion, and then wear and tear on the ductwork. In the grain industry, we don't see any rectangular duct or class 1 duct, spiral duct. We're always specifying heavy gauge round duct. Elbows need to be 1.5 radius of the diameter. So if it's a 6-inch elbow, or if it's a 6-inch elbow, it's going to have a 9-inch radius. Most dust collection applications are going to be a SMACNA class 2 or 3. The heavier, the higher the rating, the heavier gauge the ductwork is. If there's enough room, we will do 2.5 diameter radius, but most of the time there's not a whole lot of space in these grain elevators, so we're looking at a 1.5 diameter radius. Elbows, you never want to use 90-degree or mitered 90-degree elbows. Going to have product dropping out, increased abrasion, higher static pressure. With the branch fittings, I always want to come in at a 30-degree or 45-degree on a taper, and never want to come in or stub in directly to the duct. Again, going to have issues with material dropping out. You're going to have weird airflows and turbulence going on, so I want to avoid those. Mentioned earlier about needing a balanced design. Always want to make sure that we're getting the airflow we designed at each of these hoods. There's 2 methods of doing that. You can balance by design, or you can balance by blast gate. We typically see balance by blast gate in the grain industry. The balance by design, you're going to have a little bit extra airflow, but you don't have some functionalities that you do with the balance by blast gate to really dial in the hood airflows and everything else. If you are going to modify an existing dust collection system, make sure you have modeled the system to make sure the system can handle the additional processes. It's typically going to involve new ductwork from the point you've added a pickup point back to the collector. But make sure when you're modifying this that we're doing the due diligence on the front end.
Yeah, that's something we see all the time, Anthony, is people that have made modifications to their system without necessarily taking into mind the entire system itself. Or the other thing you see a lot of is someone will, manually adjust blast gates to get a result of a specific piece of equipment, where they then can have the entire system become unbalanced. So you can do it. Just ask people for help, and we can get the system to work for you. So our next system component is the dust collector itself. So the main objective of a dust collector is to filter or remove the dust from the airstream and discharge the collected dust into a container, and then send it to wherever we need to send it to. And then the clean air goes through the fan. The objective is to do this both efficiently and economically as possible, while operating in both stable and predictable fashion. The most common mistakes or things that we see that go wrong when it comes to design are, if you select the wrong filter technology for a given application. So you're using a cartridge filter when really a bag house is more effective, or you're trying to make a bin vent work as a central system or something along those lines. Another thing we oftentimes see is incorrectly sizing the dust collector. On one side, if you're too aggressive on the sizing up front, you'll end up with maintenance and reliability issues down the line. If you're too conservative on your sizing up front, you can have the upfront cost of the system be a lot more than it may be needed. And then the last thing we see is just poor installation of a system or design, whether that's a poor duct design or inlet orientation. So in this picture here, picture on the right, you'll see just that. There's a duct orientation issue as it's feeding the collector. So most manufacturers have a preferred distance of straight run that's required before you get into the collector. You can see here that there's a 45-degree angle at the far left portion of the right picture. So it goes a 45-degree angle, and then right before the inlet of the collector, there's another 45-degree angle. And what that's doing is it's having the air enter the collector in a very unpredictable fashion. And in this case, it's causing abrasion. And if you look at the picture on the left, you'll see that ring around the collector there is the abrasion from the material not getting into the collector and cycloning out correctly. So over my career, we've used many different dust collector types on the agricultural applications. And when applied, all of them work appropriately. Some can be successful, some aren't. It really depends on if you put the wrong collector in the wrong application, you can quickly get into trouble. So most commonly used are round bag houses. That's the type of showing on the left here. We use that type of collector primarily for heavy agricultural. Either they have either medium or low pressure cleaning systems, but sometimes we need a more specialty type of collector, such as what's shown on the right, where we have sticky dusts in the process or other heavy dusts where a location is not feasible to have ductwork. For the larger collectors, Donaldson's brands are like the RF, LP, RP. They can have up to 900 plus bags in them. On the right there, the more specialty collectors are for bin venting. So this is a picture of a CPV. There's a picture of a Dalmatic, and then cyclones. So we're going to talk briefly about each one of these types of collectors. The first we'll start with is the RF, which utilizes a medium cleaning system. I oftentimes recommend the RF bag house when we're dealing with very large volumes of air. We typically get up to about 100,000 CFM and then large volume of dust. They're very forgiving. They can handle upset conditions very well. It has a cyclonic action, or I'm sorry, it has a cyclonic inlet that provides pre-separation prior to reaching the filters. You can separate up to 90+% of the dust before it actually reaches the filters. These bags are cleaned on a medium pressure system that's produced by a PD blower. Thus, it saves money on compressed air. The other advantage to an RF in this type of situation is up to about 400 or so bags. It's a quick and easy installation as they come fully welded, so the units can be really lifted straight off a truck with the crane and put into place with minimal installation outside of that required. The next collector we'll discuss here is the RP collector. It's very similar to an RF. It has a lot of the similar features. It's fairly new into Donaldson's portfolio. It uses a pleated filter bag rather than fabric bags over cages. And one of the big differences that makes is the collector itself is smaller, has a little bit smaller footprint. It's shorter, less weight. So if you have an application where you have an old Carter Day unit or an old RJ or RA, this collector fits that footprint a little bit better than, say, the RF, which is quite a bit larger than this one. There's a picture here comparing the two different types of filters that we use in the bag houses. The one on the left is just a fabric bag, right? It's installed over a metal cage. During the filter change out, the entire bag and cage is removed. The bag's stripped off the cage, then the new bag is put on the cage, and you put that unit back into the collector. On the right, you have a pleated bag, which basically you just pull the cartridge out, put a new cartridge in. Pleated bags have a couple really main advantages. One is what I just suggested, is that it's significantly less time to change it out. And the second thing they can do is you can replace a 12-foot regular bag and cage with a 5 or 6 foot pleated bag, and then end up with a little bit more filter area. So that lifts the bag up out of the airstream a little more. So if you have abrasive applications or otherwise just tough issues with your dust collector, a lot of times pleated bags can solve that for you. When that medium pressure system, cleaning system isn't quite what we're looking for, sometimes we'll use a low pressure system. Donaldson's collector is called the LP. We use this on material that needs a very low can or low interstitial velocity, such as almonds or peanuts. The LP is also good. It goes up to, we can handle processes that go up to 140,000 CFM. Nothing that Donaldson makes gets close to that type of size. And last thing about this is it's a panelized version, so it can be packaged and shipped a little bit easier than perhaps shipping an entire unit. Some of the specialty collectors we use, when the traditional bag house just isn't the best option for whatever reason, we oftentimes look at the Dalmatic. In this case, you're looking at a Dalmatic G2. It's a great selection when you're dealing with sticky dusts or dusts that harden when they get moist or come in contact with moist air, such as pellets from a feed mill. These collectors have an envelope-shaped bag that has a tremendous snapping action during its pulse. You can see that on the graphic there on the left. What you get is the pulse of air and then a mechanical advantage of the bag snapping, which aids in the discharge of the dust cake. The Dalmatic also has a really true downward airflow pattern. So this helps if you have a lot of light or fine dusts. It gets it into the hopper before the air exits. This is a pulse jet collector, so it does use plant air. The next kind of collector we will occasionally use is a cyclone. Cyclone's a little different. There is no, it's a mechanical separator. It uses centrifugal force to remove, the dust, a high volume of dust from the airstream. Where this typically comes into play are some smaller grain elevators like buying points. That's what's pictured in the screen here. Or we'll oftentimes use them as a pre-separator if we're intentionally trying to pre-separate out some larger particles from smaller particles. And then the last type of specialty collector, you've seen this in several pictures already, but it's a CPV or bin venting style collector. So the CPVs are shown here. They're small, they're very economical in space. It takes a matter of minutes to change out the filters in one of these things. So Anthony, I've talked about collectors for quite a bit. You want to go ahead and talk about fans?
Yeah, Andy. So after we've designed the hoods, we've done the static pressure calculation for the system, getting the air from the hoods to the collector. Now we're going to size the fan. The fan has two jobs. We want to get the necessary airflow rate at the required static pressure, and we also want to pick a fan that's going to be appropriate for the energy efficiency and at the sound level we're trying to get at. So, for example, radial bladed fans, non-material handling fans located on the clean side of a collector are not going to be all that efficient. So we're looking at a backward curved, an air-full radial tip fan, depending on what the static pressure of the system is. Some common mistakes we see: poor fan selection, whether that selection is at the peak of the fan curve, or poor fan installation, where you've got an elbow right into the inlet of the fan. The static pressure, and this is a very, very simplified system, and we've talked a little bit about, we've got to balance the static at our branches to get the actual static pressure of the system. Very simplified system here. Got a 1.5 inch static pressure loss through our hoods, 3.5 inches through our ductwork, and then 6 inches across our filters. We always size for 6 inches across the filters. That's typically the point where we're telling customers to change their filters. Anything over that 6 inches, you're going to start getting material or dust pulled through the filter itself and going through the exhaust. So for this system, we're doing 9,000 CFM at 11 inches. Donaldson has TBI fans. So if you have a fairly simple system, these fans bolt directly to their collectors, very easy to use. So to size this fan, we're going to use the static pressure of 11 inches and the airflow of 9,000 CFM. We're going to line those factors up. And you can kind of see it's going to fall between the TBI 25 and the TBI 30. Always going to select the TBI 30 to make sure we have enough airflow when the filters get dirty. We'll either have to damper the fan back, or we'll have to use a VFD to adjust it down. With a lot of the explosion protection stuff, you're going to have additional static pressure, and that's something we've got to also design for. It's not included in this right here. To finish things up, and then we'll open it up for some questions. There are a few other design considerations to think about, and Andy and Charlie kind of hit on this: the total cost of ownership. What's the energy cost, compressed air usage, PD blower, the fan energy, freight and installation of the collector itself? Where's it coming from? How easy is it to get parts? How long do the filters last? And how easy is it to change the filters out or maintain the system? And then what's the expected life expectancy of the system? Another consideration I wanted to mention is how technology is being used to monitor dust collection systems. So Donaldson came out with their IQ device several years ago to make dust collectors smart. This device gathers process data in real time, creates automated alerts and historical reports, and it's available to customers at no charge. It's a great way for process owners to manage and track regulatory compliance information. So your monitor static pressure when EPA or in Alabama, it's the ADEM comes out and wants to see the differential pressure of the collector. That information's all stored there. It also helps you troubleshoot dust collection issues more efficiently. Then regulatory considerations. So there's a lot of agencies involved in this, and each of these agencies have design expectations to reduce process-related hazards. Knowing the hazards related to the process the system is designed to handle will enable you and the customer to make some critical design decisions up front in the process. If you've ever had to go back and modify an existing system, it is very time consuming, very expensive to do that. NFPA is the global self-funded nonprofit organization devoted to eliminating death, injury, property, and economic loss due to fire, electrical, and related hazards. The standards developed by NFPA are called consensus standards because they are widely recognized by authorities. OSHA considers NFPA standards to be good engineering practices, and during a general safety inspection may reference NFPA standards when issuing fines to a facility under the general duty clause. There are a lot of different NFPA standards related to combustible dust. The starting point's NFPA 652, the fundamentals of combustible dust, and this will point you to the industry specific standards such as 61 for agricultural and food processing facilities. There's a new NFPA 660 coming out. It's supposed to come out this fall. It may be coming out next year now. That is going to take all of the industry specific standards and put them into one standard. 68 and 69. 68 is the standard for explosion vents. It's where it talks about how to size those explosion vents. And then 69 is the standard on explosion prevention systems, where it talks about the different equipment and other things out there to do that. Some different mitigation options: explosion vents, no return valves, rotary airlocks that act as a material choke at the bottom of the collector. Depending on the application, the authority having jurisdiction, the AHJ, and the process owner's risk tolerance, you may use one or all these different options. One thing about the no return valve, it is going to add additional static to the system, typically in the 1 to 2 inch range. So your fan has to be sized for that. So if you're going back and retrofitting, you may have to change your fan out as well to keep your performance of the system.
All right, thank you for all that detail to the featured speakers. Great job. We understand that designing dust collection systems is very complicated and a lot goes into it, but that's why we're here. We've sold countless dust collection systems around the world, and we're happy to support you in your local market. So we're always here to help. As we wrap it up and we get into the next Q&A session, presenters, you can turn your cameras back on. Just a heads up, everyone who did attend will receive an email with their professional development hour credit. We're going to put a link in the chat box to our webinar page where you can watch various webinars that we've put on, usually monthly, and we'll have this recording up as soon as possible. If you have follow-up questions, my email's here at the bottom of the screen. You can send me an email and we'll make sure we get back to you. So Amy, what is our first question?
Anthony, this one's probably for you. Does balance mean the same velocity in both branches or in all branches? Asking about what exactly do you mean by balancing the system?
So it's typically related to an airflow velocity that we're looking at. So we want to make sure we're getting at least 4,000 feet a minute in each branch. That's kind of one of the standards for combustible dust. But balance means that the static pressure is balanced at that junction point. So we're applying artificial resistance through the use of blast gates to make those static pressures balance at the airflow rates that we've designed it for.
So this is kind of a follow-up question to that. So the next question is, do you typically fix or weld the blast gates in place after the system is balanced? So how do you make sure it stays that way, I think is the question.
Yeah, so the blast gates typically come with a set screw, and when I say set screw, it's a pretty beefy bolt that holds the blast gate in place. We typically don't weld them. There may be some process changes that happen over the years where we're going to need to rebalance the system, make some small adjustments. With the blast gates not being directly at the hood, they're less likely to be changed by the operators at the plant. If the blast gate is right there at the hood, which we don't recommend, it's more accessible for them to change it. But a lot of times our blast gates are in places where you would need harnesses and maybe even scaffolding to get to set those gates.
All right, so our next question, how important is it to use a quality ducting product? Is spiral okay, or is third-party tested quick clamp ductwork better?
We typically see flange ductwork in the grain industry. Spiral's going to have leaks over time. The quick clamp, we use quick clamp a lot in a lot of different industries, but with the grain industry, with it, the amount of dust going through the ductwork, we're typically in a SMACNA Class 2, SMACNA Class 3 heavy gauge flange ductwork, and it's just there's a lot of vibrations in these facilities. There's a lot of different things going on. We've just had better success with the flange ductwork than the quick clamp. And that's kind of what the customers expect. That's what the folks in the agricultural industry are used to seeing and have had great success with.
Thank you, Anthony. All right, so next question. In the ductwork area as well, is a 3-inch diameter centerline radius overkill?
Yeah, so, I saw that question come up and I pulled out the vent manual. The elbow loss coefficient for a 1.5D elbow is 0.24, 2 inches, 0.19. This is of the VP. So whatever your velocity pressure is, you multiply that out, and then 2.5D is 0.17. So there's really not a whole lot of advantage from a 2D to 2.5D. What you are getting though is some reduced abrasion. The majority of the systems we do are going to be 1.5D radius elbows. And it's really more of an issue of space constraints within the grain elevator itself.
Thank you. Let's see, Andy, this one's probably for you. So when would you recommend, it's asking a blower versus compressed air, but maybe when would you recommend like a baghouse that uses a PD blower? And when would you recommend one that uses plant compressed air? Do you have any specific guidelines for that?
Yeah, I mean, really, there's 2 things we look at. One is the overall volume of the system. Typically, when you get in larger systems, more CFM, it becomes more economically upfront and long term feasible to use a larger baghouse like an RF. And then the second thing we tend to look at is the grain loading of that system. So if we're in a system that has a very heavy dust application, or there's room for upset conditions, we typically tend to use a baghouse over a cartridge collector that would use compressed air.
All right, thank you. All right, next question. How would you handle ducts that penetrate rated walls for assemblies?
With that, we're getting into structural calculations and everything else. We partner with third-party engineering firms in scenarios like that to do the detailed design of how to penetrate the walls, to give us actual design so that we can do that. We've seen a lot of at grain elevators, a lot of ducts that go through windows, and they've gone back and framed around it because of that issue. I can think of a handful of them we've seen do that over the years.
All right, Andy, are you seeing the question that came in at 10:54? For multiple pieces of equipment connected to a common dust collector, please comment about the use of a VFD for airflow control, assuming one or more of the pieces of equipment are not operating while the other equipment is operating. While they're good to reduce amperage, the use of VFD can be problematic for transport velocity.
I'm going to jump on that one if you don't mind,
Yeah.
Andy.
Go ahead.
So with our dust collection systems that we are doing in the grain industry specifically, we're making allowances so that we can pull air from each point at any given time. VFDs we do use a lot, and it's more for compensating for when the filters are clean and then the filters get dirty. So once the system's balanced, it's been put in place. Donaldson has this great piece of equipment called the airflow controller, where we'll take the static pressure on the dirty side, which we can correlate to an airflow once we balance the system. And as the filters get dirty, it will speed the fan up slowly so that we're getting a constant volume at all times. So as those filters go from 1 inch of differential pressure when they're first installed to 4 to 5 inches towards the end of its life, a year and a half later, that VFD is going to slowly speed that fan up to compensate for those the differential pressure across those filters. We also use that with the compressed air filters that are going typically between 2 and 4 inches. It doesn't always clean. They have a Delta P plus, so as the filters get dirty, it'll go up to 4 inches of differential pressure. The compressed air filter cleaning will kick on. It'll go down to 2 inches, and that VFD is just maintaining a constant volume based on the dirty side static pressure to keep it there.
Thank you, Anthony. All right, so this is the last question that we have in here at this point anyway. If anyone else has any more, we got about 2 minutes left. You talked about improved elevator dust collection from the outer side of the trunks. Do you recommend doing it from the inside between the trunks?
There's still a lot of those out there. We do recommend going up on the casing. It's a little bit different than what the manual recommends. But there was some research done back in the 80s that talks about moving those pickups up the leg that allows the grain time to settle. A lot of these elevators are fed from the back side, so the buckets as they go around are actually having to scoop the material as it comes around, and that causes grain just to go everywhere inside that boot. So by moving the pickup point a little bit further up, it gives that grain time to settle in the buckets to where our dust collection pickups aren't pulling the grain into the system, and we're just getting the dust. So we can pull a little bit harder further away from where all that dust is generated to get dust out of the bucket elevator.
Thank you, Anthony. Well, thanks to all of our speakers today. Thanks for all of you who attended. Great questions. We'll make sure and follow up with a link to the recording once it's available. And also you're going to receive your CE credit by email very shortly. So thanks, and hope everyone has a great rest of your day.